right.
Okay, so let me okay, so in this talk I will introduce some of the joint works with Kowei Chen and Conan Liang from Chinese University of Hong Kong on hinting connections in geometric quantization and deformation quantization. So I will talk about the following. My talk will be consists of the following four parts. The first one is a very quick introduction of geometric quantization and hitching connection. The second is deformation quantization and algebraic index theorem, which is the starting point of these projects. And the third is Kähler quantization by Kapranov's L-infinity structure. And then the last is the main result on quantum master equation and the hitching connection. Okay, so let me start from geometric quantization and Toeplitz operators. So on a Kähler manifold, basically it means it's a symplectic manifold with a compatible complex structure. So the Hilbert space of level K of its geometric quantization is defined as the following space of holomorphic sections of the K's tensor power of the so-called pre-quantum line bundle, which we denote by L. On these Hilbert spaces, which we denote by HK, we can define the Toeplitz operators associated to a smooth function. So basically, this is the idea coming from canonical quantization. Say we start from something classical and we want to quantize that. So the classical object are smooth functions, and then the quantum objects are certain operators. So these are called Toeplitz operators. Here, MF denotes the multiplication by a smooth function, F on X, and here pi denotes the orthogonal projection from the space of smooth sections of L to the K to the closed subspace of holomorphic sections. So this is a definition of these operators. So obviously, if you quantize a function to an operator, in general, it's not, well, if you look at the classical multiplication of functions, then it's commutative. But if you look at the composition of these operators, then it's not commutative at all. And so we have the following asymptotic formula for the composition of these two Toeplitz operators associated to F and G respectively. As K goes to infinity, the asymptotic behavior is as follows. So the first term, you can see that it corresponds to the classical pointwise multiplication, which is commutative of F and G. And then we have the following, the so-called the quantum parts. And it's the following expansion in 1 over K. Here, these CIs are bidifferential operators applied to F and G, meaning that these are local in the sense that it only depends on the pointwise the jets of these functions. So this actually gives rise to a so-called deformation quantization of smooth functions on X. But if you turn 1 over K into the formal variable H bar. So in particular, if you look at I equals 1, and it actually gives you, if you look at the commutative product at the I equals 1 level, then you will see the Poisson bracket. But here it's not only Poisson because you have all the higher order terms in general. So what is a deformation quantization? So it's an associative but non-commutative deformation of the algebra of smooth functions on symplectic manifolds. So you can say that it's a model. It's actually a model for operators, for the algebra of operators in a quantum system. So the precise definition is as follows. So you start from a symplectic manifold M with symplectic form omega. Then a deformation quantization is an associative product, which we also call star product on this C infinity of M with a formal variable H bar, such that F star G equals Fg, and then you can see that it's of the same form we have seen in the previous page, where these CIs are bidifferential operators with C1 Fg minus C1 GF equals the Poisson bracket, which is actually reflects the symplectic structure. Okay, so now this actually in this construction, so we have seen that we need to use the additional structure of a polarization. So here we are using complex polarization. So mathematically, it means it's a complex structure which is compatible with the symplectic form. So you can see in the definition we have used this complex structure because we are using holomorphic sections. So that already involves the complex structure. So actually a natural question arises from this choice. So how to describe the independence of geometric quantization on this choice of a compatible polarization? Because if you look at the classical mechanical, the mathematical structure in encoding this classical mechanics, it's only about the symplectic structure. But now in this construction, we are using the complex structure also. So we have to show that this construction, so it's reasonable to require that your construction should be independent of the choice of the complex structure. And we can actually formulate this question mathematically as follows. So suppose you have a parametrization space T of a family of compatible complex polarization or equivalent complex structures on X, compatible complex structures. Then the Hilbert space H0 xt of L to the tensor power K. So because this H0, I didn't write down this D bar here, this D bar now depends on this T in this parametrization space. So it actually forms a vector bundle over the parameter space T, where the fibers are simply these Hilbert spaces for each fixed complex structure T. And the standard differential geometry tells us that a connection on this HK actually induces a parallel transport between these fibers, I mean these fibers which are Hilbert spaces. However, this parallel transport, we know in differential geometry that it depends on the choice of the path you choose between different points on these parameter spaces. So in order to identify the fibers of HK in a canonical way, we need a flat connection. So actually, we actually need a projective flat connection. This actually corresponds to the fact that in quantum mechanics, so the important thing is not a vector in the Hilbert space, but actually a vector, a non-zero vector modular the scalar in this Hilbert space. So this projectivity actually corresponds to this procedure of modular those scalars, non-zero scalars. So to understand the role of a flat connection, so we may compare it with the Durham differential, right? That's something standard in calculus. So so the Durham differential actually detects constant functions, right? So you want to say that a function is independent of the points. Is a constant function means that it's independent of the points on a space. So you apply the differential, Durham differential, and it tells you that if it's annihilated by this Durham differential, then it's a constant function. So this is similar, but now in a more complicated way. We want to say that some structure is independent of a choice. Then you should construct something similar to the Durham differential. And you also want to say what kind of things are corresponding to the constant things, and those things are actually what you really want to find. So let me say a little bit history about hitching connections. So the first and most important example of hitching connection is given by Hitching and Axel Del Pietra and Witten in Chern-Simon's theory, and it was later proved that actually the hitching connections they constructed independently are actually equivalent. So there has been studies on more examples of hitching connections. However, so to our best knowledge, there was no systematic theory of the study of hitching connections in general quantum theories, including its existence and properties. So, for instance, in the example I just mentioned, in Chern-Simon series, it's actually a very important part of their work is to construct the hitching connection. So the idea of our works is actually to use the theory of deformation quantization to give a systematic study of hitching connections. So this is something we didn't see in the literature. And as as we study more on the quantization of symplectic and in particular Kähler manifolds, we realize that we should require that hitching connections satisfy an asymptotic property with respect to the level K of the Hilbert spaces. So there are two reasons for this consideration of looking at this asymptotic behavior. So the first one is that the hitching connections for Hilbert spaces of different levels of K positive should be related to each other, meaning that you have K equals 1, K equals 2, and until K goes to infinity, all the positive integers. They should not be independent, but they should be related. So if you look at the construction of Brazilian-Topliss construction, Brazilian-Topliss operators construction, so this is totally reasonable. And the second one is hitching connection. So it's a notion for both quantum observables, or equivalent is the algebra of quantum operators, and also Hilbert spaces in geometric quantization. And the algebra of quantum observables, we have said that they are given by Brazilian-Topliss operators. They are actually described in the asymptotic as K goes to infinity. So these are the two reasons we should actually refine the notion of hitching connection. So if you look back to the original construction, they simply set K equals 1 and they start their construction. But now we are doing not only for K equals 1, but actually for all the positive integers. So let me explain something in the title of my talks, that is and also the abstract, that is Bettling-Viekovsky quantization. So a brief history is as follows. So it is known that the mathematical difficulty of quantum field theory involves the infinite dimensional path integral and the Bettling-Viekovsky formalism, which we will call BV for short. This actually arose in the end of 1970s as a tool of mathematical physics designed to define and compute the path integral for gauge series. And in this formalism, the key ingredient is the quantum master equation describing the quantum gauge consistency. So there is actually a mathematical model for the path integral using homological algebra and the technique of Feynman graph computation. So to model the following not well-defined infinite integral on infinite spaces. So here, this curly E here is a space of fields, which is in most cases infinite dimensional, and capital S is the action function. So basically, this is a way of modeling this integral in a combinatorial way using Feynman graph computation. So in a joint work with Ryan Grady and Li, we constructed a sigma model which target a simplex manifold. This is some work in 2015. So on simplex manifold X, we consider its quantization in this BV formalism. So another technique we used is the so-called compactification of configuration spaces. And we can show the following theorem is that, first of all, the quantum master equation in the BV formalism of the sigma model is equivalent to the flatness of the so-called Fedosov connection in the study of deformation quantization. And the second main result is the associative algebra induced from the factorization algebra of quantum observables is isomorphic to the Fedosov deformation quantization on the simplex manifold. So actually in this work, we give a very clear understanding of deformation quantization as the algebra of quantum observables. Another part of this work is we can also define the correlation function. So as we in the introduction of the BV quantization, we said that we have a mathematically rigorous model of the path integral using Feynman computation. So actually in this work, we fully use this technique.
Excuse me, from Nagoya side. My name is Hiroaki Kanno, and I'm going to present what is the master equation.
Mm-hmm. Okay.
I mean, you are several in the previous slide. Your theorem is quite abstract, and I'm wondering what is. I mean, or maybe most of the people don't know what is the quantum master equation, and so could. Well, if you are going to tell us about what is the quantum master equation, it's okay. But if you don't, could you explain what is it? And also another question is here appears H bar.
Mm-hmm.
H bar, and in the previous your presentation, H bar H bar is just 1 over k. K is the level. In this case, you just consider only sigma model. Sigma model.
So that's actually two stories here. So in one story, H bar is a formal variable. Mm-hmm.
You are telling two stories together.
Yes.
No, yeah, okay. So okay. So could you explain what is the relation to your previous? I mean the program of geometric quantization and its relation to quantum master equation.
Yeah. So yeah, I'll actually say that more later. Yeah. So I will explain that. So because as we yeah, so one of the reasons I didn't want to say too much about quantum master equation is this result. Yeah. So we proved that the quantum master equation is actually equivalent to Fedosov the flatness of Fedosov connection. So that's so I want to simply use Fedosov equation instead of the quantum master equation with using this theorem. Okay. So is that good? Yeah.
Please proceed.
Okay. Yeah. So let me say a little bit about this 1 over k and h bar. So there are actually two stories. One is in geometric quantization. So here we have L to the tensor power of k, and yeah. So let me say this here. So this is from the geometric quantization and the theory of Brazilian Topli's operators. So you have to look at this asymptotic property as k goes to infinity. And this, so if you turn this 1 over k to a formal variable h bar, and you will get an associative product. But now the price is that you don't have the exact value of 1 over k, but you only get something formal. So this formal thing actually comes from this asymptotics as k goes to infinity. Yeah, so so this is from geometric quantization, and also here if you start from if you only look at the algebra of quantum observables, and you will, so we simply start from something formal, and we just make this definition here. And the point is that if the Brazing-Topliss quantization gives rise to a deformation quantization in this definition. So that actually, yeah, I should say the geometric quantization or Brazing-Topliss quantization and also Fedosov quantization are two main techniques to construct these both the Hilbert spaces and this algebra of observables. Okay, yeah, so let me continue. So another part of this work is we can rigorously define or rigorously give a model for the path integral, and which is completely computable. So we can define the correlation function in the following homological way. So we start from quantum observables, as I just said. It's actually isomorphic to smooth functions on X with this formal variable h bar, and we can actually do some Brazing integral. Which I will not go to the detail, and we can do this Brazing integral, and we end up with something in the de Rham complex. And because it's actually there are actually differentials on both sides, and this Brazing integral is a cochain map. So you end up with something, so you start from something close. So this is actually the cohomology here. So meaning that you actually get something close, and you take the map of the Brazing integral, you also end up with something close. And that's how you actually end up with this map actually goes to this de Rham cohomology of M. And with this de Rham cohomology, so we can do this standard integral on M, the integration of differential forms, and you end up with some number. Here still you have this formal variable h bar. So that's how we define the correlation function of these observables. Now, this correlation function actually satisfies two properties. So first one is the leading, if you look at the leading term, so that's the standard, that's the classical, volume. Namely, you take F times the Liouville volume form and you integrate, but there are like higher order terms in this H bar expansion. And second one is the correlation function of a star product is actually independent of the ordering. Namely, you take F star G and takes the correlation function is equal to the correlation function of G star F. And that's the reason we call it a trace. You just think about the trace of matrices. The most important property is so the trace of A times B is equal to trace of B times A. So that's the reason we call it a trace. And we actually by using this Feynman graph computation, we can actually get an explicit formula for the partition function or the correlation function of the constant function of 1. And it turns out this is given by the following formula. So you may see that this is quite looks quite similar to the formula in index theory. And actually, people prove that they are actually equivalent. And this is called the algebraic index theorem. Okay, so this is some old story, and these results. So they date back to 2015. So they are still not completely satisfactory for us, since we only see in these work the quantum observables. which describes the algebraic structure of operators. But the Hilbert space is absent in this picture. Now, but we know that the mathematical theory of the Hilbert spaces, also known as geometric quantization, is completely missing. But if we want to see the geometric quantization, we also need the data of polarization. So that's the reason we focus on the case of Kähler manifolds. So there are two main types of polarizations on a symplectic manifold. One is real polarization, another is complex polarization, and also you have a mixed polarization. So the goal is to give a quantization scheme in the BV quantization framework, which encodes both the quantum observable and the Hilbert spaces. So that involves in finding a particular quantum mass equation or equivalently Fedosov equation in this Kähler setting, which should be compatible with both the symplectic structure and also the complex structure. And the interesting thing is that it's closely related to the structure of the so-called L-infinity structure. So this L-infinity structure was discovered in 1996 by Kapranov in his study of the Rosansky-Witten theory. So the main ingredient of this structure, of course, you have different equivalent ways of describing this L-infinity structure. So one convenient way is to describe it as a cochain complex whose cohomology is actually isomorphic to holomorphic functions, which actually gives an equivalent description of the complex structure on X. So this is something we didn't expect from the beginning. So the theorem we proved is that there exists a Fedosov flat connection D on X, which is a quantum extension of Kapranov's L-infinity structure on Kähler manifolds. So why is it a quantum extension? So I may say one or two sentences about this. So as I just said, the original, this L-infinity, or the classical L-infinity structure is isomorphic. So its cohomology is isomorphic to holomorphic functions. So which means that it only depends on half of the functions, meaning those holomorphic functions. So very roughly speaking, well, maybe a little bit not strict, is that so if you want to see smooth functions or maybe and real analytic functions, so you better have not only holomorphic functions but also anti-holomorphic functions. You should combine them together. And so we can find actually a quantum extension of this Fedosov connection, or equivalently a quantum mass equation. So that actually that can be described. That can describe all smooth functions. So this is something. So in the computation, you will see that this is very simple. So simply some linear algebra. But the result is very interesting because according to these results, so this Fedosov connection actually induces a BV quantization of the Kähler manifold X. And its construction is completely different from Fedosov's original construction in around I think also around 1996. And this quantization, because it's constructed as a quantization of this L-infinity structure, which arose from this complex structure. So this quantization scheme encodes not only the symplectic geometry, but also the complex geometry of this Kähler manifolds. This is a very natural candidate. So now I'll briefly describe this Fedosov connection, or equivalently the quantum mass equation. So it looks as follows. So this is nabla because you have the Kähler structure. You have a canonical Levi-Civita connection, and also you have some corrections which is gamma bracket something. And this is the most interesting thing, because so if in general on a Cantor manifold, you take the square of this connection, or equivalent is a curvature, it's not zero. So you have to add something which is which we call some quantum correction, which makes it actually flat. So here this bracket denotes the Lie bracket associated to the weak product on the so-called Weil bundle. So there are some details which I cannot explain. So the flat sections under these connections are actually isomorphic to quantum observables. So this is quite similar to Fedosov's original construction. And the interesting thing here is we can actually extend this construction not only to the bundle of algebras, but we also have a construction we can extend this Fedosov connection to the module sheaves. So here so in this way, we not only have we can describe not only the algebra of quantum observables, but also the Hilbert spaces, where the Hilbert spaces are simply described as modules over these algebras. So we can actually prove that. So we simply extend these Fedosov connections on the Weil bundle to Fock bundle in a compatible way. So the compatibility is saying that if you take the connection acts on some, so alpha is something in the algebra and S is something in the module, and you have the compatibility in the obvious sense. And interesting thing is, in this case, so we can take the evaluation of H bar equals 1 over K. So that so at the beginning we are always worried about this how we can like try to balance between this formal variable and these exact values 1 over K. And because of the special property of these Fedosov connections, so we can actually take the evaluation here. And it turns out the flat sections of the Fock bundle is isomorphic to the Hilbert spaces in geometric quantization. So this is somehow we can actually combine them together. I mean, both deformation quantization and the geometric quantization. So that's actually the foundation. So why we can use the technique of deformation quantization to the study of geometric quantization, in particular the Hitching connection. So to work in the case of to work on the Hitching connections in geometric quantization, so we have to consider families of complex structures, meaning that so in all the previous construction, so we have fixed a Kähler structure on a manifold X. Namely, it's a complex structure compatible with a symplectic form. But now we have to understand the case that, so we have T, which is a space of a parametrization, which are parametrizations of a family of complex structures compatible with the symplectic form on X. And in this case, we can simply take the pullback, because the Weil bundle is actually is a complexified Weil bundle, is independent of this complex structure. So we can simply take the pullback to this family, to the family space. This is simply X cross the parametrization space T. And so we can also so this is like so we take the pullback, so that's the Weil bundle in the family case. And we can also construct the module Fock bundle in this geometric setting in a similar way, but a little bit more complicated. So now the quantum master equation in families. So we have a reasonable Fedosov connection in the family case. So it should involve not only those DTs, I mean those Fedosov connections, for each fixed complex structure, but also an operator in the t direction, which describe the variation of complex structure. So this is also the core part of this series of hitching connections. So the reason we need fiberwise Fedosov connection is very simple, because if you take the cohomology of these fiberwise Fedosov connection, it gives rise to the Hilbert spaces by our theorem. Okay, and so we will consider those flat Fedosov connections on wire bundles in family, which are of the following form. So we have dt, which is a de Rham differential along the t direction. And we also have this capital D with the subscript little t here, which is a fiberwise Fedosov connection. And then we have this capital A here. Now, this capital A here is actually a differential operator on the wire, and also actually it can act on the fork bundle. So it values in one forms in T. Now, the theorem we can prove is that an asymptotic hitching connection is actually equivalent to a quantum master equation in the family fork bundles on X cross T. So now in this case, the quantum master equation is not only describing the fiberwise behavior of the sigma models we constructed before, but also how these sigma models, the correlation functions, the partition function, and the quantization, the procedure of quantization, how it depends on this parameter space. So if you want to get a model which is most ideal, is that it should be independent of the choice of the complex structure. So that basically means you want to find such a connection which is totally flat. So because this is something on X cross T, so you take the square of this operator, you will have several terms. So for instance, you have this dt, which is along the X direction, and obviously this square is 0 from its construction. And also you have these terms, which is one form on X and one form on T, which comes from the commutator of dt plus A with this capital D little t here. And you want this to vanish, and it also has a very clear geometric meaning. It simply means that because this dt plus A is describing this parallel transport along the t direction. So if you have these two parts commute with each other, it's basically saying that, so when you do parallel transport, it actually preserves the subspace of cohomologies. So that means it preserves the subspace of Hilbert spaces consisting of holomorphic sections. So in this way we can so the hitching connection, the problem about hitching connection, and actually well, I didn't say much detail about this asymptotic hitching connection, which is more reasonable. And this asymptotic hitching connection, all the problems about these asymptotic hitching connections is now turned to the problem of quantum master equation. For instance, how can we find that, the existence and those properties? And another important thing is that because the hitching, the quantum master equation in this case is defined on both the wire bundle and the fork bundle. So on both wire bundle and fork bundle, it means that it describes the compatibility between wire and fork. So that's the algebra and Hilbert spaces. So that actually relates deformation quantization and geometric quantization together. Okay, so and another question, of course, is so how you can find such a flat connection. So I will describe a little bit on how you can algorithm of finding such a flat connection. So the which can be the first step is we want to find some nabla, we call nabla T, that's dt plus A1. So this is like a step-by-step construction. So we want to make nabla T square equals 0, and nabla T is compatible with both the weak product and the Bachmann function in the obvious sense. Okay, and so this is the first thing. And in this way, we obtain asymptotic hitching connections for both Hilbert spaces and quantum observables. Okay, so another thing, so we have to still find we have to meet the another vanishing, which is the idea is to make certain corrections to this nabla T. So nabla T is the first step. And we can show that this correction is possible if the family of complex structures on X satisfies a certain geometric condition, which we call a higher rigidity condition. And the condition that the cohomology class of the Ricci forms are proportional to that of the symplectic form. So, and this is the second step. And the last step is to look at the term, which is a two form, the part of the curvature, which is two form on T of the curvature. So that's actually equivalent to the projective flatness of the associated hitching connection. And what we can prove, what we have already proved is that suppose the family of the complex structure satisfies the above geometric conditions, for instance, the including the higher rigidity condition and also the condition on the Ricci form, then there exists a Fedosov connection nabla T plus A2 plus DT if the following Moore-Cartan equation is satisfied. In other words, so the projective flatness is turned to a solution of the Moore-Cartan equation. And so in this way, so if you look at the Moore-Cartan equation, you will see actually a series of homological obstructions to the existence of flat asymptotic hitching connections. So that's actually something, the next step is something we are still working on. And we can already specify these obstructions in certain cohomology groups. Yeah, so I'll just stop here. Okay.
Thank you very much for your very interesting talk. And is there any question or comments from Nagoya? So Kano Sensei have some question.
Excuse me, again from Hiroaki Kano. I'm still wondering, what do you mean by the quantum master equation? Is it same as, in your terminology, is it same as a Fedosov connection?
Yeah, so in our model, in our model, the quantum master equation is actually equivalent to the Fedosov equation. So
that's different from my understanding. I mean, okay, so you use quantum master equation is that same as the Fedosov connection?
Yes. Yeah.
The question is, do you have a concept of a classical master equation? Not quantum.
Sorry, can you say again?
Master equation. Usually, my understanding of PV quantization, we originally some kind of classical master equation, and then we get quantum master equation. If your quantum master equation is the same as Fedosov connection, what is the classical analog?
What is quantum?
No, classical analog.
Oh, you mean classical master equation?
In your sense?
Okay. So if you look at so Fedosov equation in this case is simply d squared equals 0, right?
Just a flat connection?
Yeah. So yeah, the Fedosov connection. So
Yeah.
so if you look at the equation modulo h bar, it still vanishes.
Yeah.
Yeah, so that part is actually the classical part. So that's the classical master equation. And basically, a quantum master equation is you have to do corrections. You have to do like order by order corrections in the power of h bar. Yeah, and actually, that's how originally Fedosov can solve his equation. So he basically like try to like annihilate those non-zero terms order by order. Yeah. So the starting point is actually the classical master equation, and actually there is a so if you because quantum master equation is describing a certain gauge consistency here. So there is the gauge consistency in this sigma model. Basically, it's because we are doing this. So we are mapping S1 to the symplectic manifold. So what we do is we actually try to linearize the target space around each point. So at each point you have certain expansion of that, but then you have overlaps of neighborhoods of different points, and then you should have certain consistency, and that's actually the gauge symmetry in this model. And the classical master equation is describing this gauge gauge symmetry here.
I see. Thank you. The additional one more question is, in my understanding, the quantum or classical master equation, in my sense, involves so-called BV anti-bracket, which is something like odd symplectic structure.
Yes. Yes.
Do you have similar odd symplectic structure in
Yes.
your formalism?
Yes. It's not so obvious if you look at the Fedosov equation, because so actually if you look at our paper, I mean my paper with Ryan Grady and CD, so we actually have S1 maps to a symplectic manifold. Okay, so if you have a map, if you try to linearize that, you have certain functions. Okay.
Yes.
But in that case, you also have anti-fields which are actually one forms valued in the wild bundles on the target, and actually they play the role of anti-fields and anti.
I see. So in any case, you have a concept of anti-field.
Yes.
But I mean, it is rather implicit in your.
Yes,
I mean,
it's rather yes, it's indeed implicit if you only look at the Fedosov equation.
Okay. Thank you.
Is there any other question online? No. Then let me ask one naive question. I'm Yanagida from Nagoya. So your theory is very interesting in the point that it involves both symplectic and complex geometry side. By the way, we have there is the so-called generalized complex geometry. It is in some sense an interpolation of complex and symplectic geometry. Yes. Maybe we can consider some deformation quantization of such a generalized complex geometry. Do you have some?
That's some. Yeah, I think that's something very interesting. Although we didn't consider that before. Yes.
Yeah. Oh, really?
Yeah, I think it's very interesting because generalized complexure involves both complex and so it's like a combination of complex and symplectic structure. Yes. Yeah.
Anyway, thank you very much for the comment. No question? No other question? Then let us thank the speaker again. Thank you very much.
Thank you.
The next talk is a final talk, so please. Yes. And then let us start the final talk of this workshop. The speaker is Hattori-san from Nagoya University. And he will talk on the algebraic structure of elliptic quantum groups. So please start.
Thank you for introduction. And this is Hattori from Nagoya University. I'm studying quantum algebra, and it's the representation theory. So I'd also like to thank the participants and awareness committee of this valuable opportunity to talk here today and this virtual workshop. Thank you so much. So in this talk, the title suggests, I will talk about the algebraic structure of elliptic quantum groups. So, and this is the outline of this talk. First, we recall the dream-fed realization of quantum-affine algebras, and secondly, we define the elliptic quantum groups and give a brief review of its Hopf algebra-like structure, in particular, dream-fed type co-multiplication. And finally, we define the so-called H-Hopf algebra and explain how the elliptic quantum groups possess this structure. So this is a conceptual diagram of related topics. So it is well known that the so-called Yang-Box-2 equation is an important object in statistical physics and mathematical physics and many other fields. So, and there exists a well-known class of the solution consistent of the hierarchy of what can I say, rational L matrices and trigonometric L matrices and elliptic L matrices. So here, I mean the hierarchy, the trigonometric ones reduced to rational ones, and elliptic ones go to trigonometric one if we take some limits. So, and it is well known that trigonometric R matrices are governed by some kind of Hopf algebra and quantum affine algebra. Where Hopf algebra means some additional structure on algebra that is co-multiplication and co-unit and anti-Hopf. So it is natural to expect there exists kind of elliptic analog of the quantum affine algebra, such that describing the structure of elliptic L matrices. And the answer is yes. This is the elliptic quantum group in right above box. So this is today's main topic. So, studying this elliptic quantum group led to the whole, what can I say? So, comprehensive understanding of the hierarchy of these R matrices. So, I think this research is important. Okay, so to begin with, we recall the dream-fed realization of quantum affine algebras. As I mentioned about in the previous slide, a quantum affine algebra is a kind of Hopf algebra associating with affine root systems. And it has an application to Yang-Box-2 equation and solvable lattice models and etc. So, and dream-fed gave the loop algebra-like realization of this algebra and generators and relations like this is over here at the bottom. And it's so complicated as you can see. However, if we introduce a current, in other words, generating functions of generators, we get much simpler presentation of this algebras. That is, we define the current as a formal power series over here as the middle, and define the exchanging relation of these currents as follows. Where these relations are read as a formal power series in Z and W, and expanding both hand sides and comparing the coefficients, we can recover the original defining relation of generators. And it is interesting that these relations, exchanging relations of currents, written in terms of so-called structure function Gij affine Z, a simple rational function. This function admits interesting property that is Gij affine inverse Z is equal to the inverse of Gji affine Z. And this property is crucial to endow the algebra with a Hopf algebra structure. So in particular, the co-multiplication is like this, written in the current form. This is called Drinfeld co-multiplication. So extending this realization elliptically and dynamically, we read the notion of elliptic quantum group in the sense of Jimbo, Kono, Orake, and Shiraishi. This is a kind of graded algebra with quantum parameter Q and elliptic norm small p and dynamical parameter large P1 large PL. And the ground ring is C double bracket P, formal power series in P. And its structure function is kind of theta functions, defined like this. These functions are reduced to structure functions of quantum affine algebra if we take the formal limit small p to 0. And I will explain briefly the dynamic parameter. So let a half pi pi j be a realization of a finite, and not a finite root system XL. And set the symbol large P1 large PL as a dynamic parameter, and define the 2L dimensional C linear space H hat spanned by dynamic parameter large PI and so-called shifted dynamic parameter large PI plus alpha I check. And denote the field of meromorphic functions on H hat star, dual space, I mean, by M H hat star. And define this field as a generator. We can install this dynamic parameter and shift the dynamic parameter into the elliptic quantum group. So I will explain this point a little precisely. So elliptic quantum group is defined as follows. These generators currents like this. There's no need to see these relations clearly, but anyway, it is important to that if we take a formal limit small p to 0, all of the notions are reduced to the one of quantum affine algebras. So in this sense, we can insist that this algebra is an elliptic and dynamical analog of a quantum affine algebra. So we can also define a Hopf algebra-like structure on this elliptic quantum group if we introduce a modified tensor product, tensor children. And the co-multiplication is written in a completely similar way as a quantum affine algebra case. So any other question till now? Okay, so let me see. So to explain what Hopf algebra-like structure on elliptic quantum group is, for some time we work in more general setting. So in other words, I will introduce so-called H-Hopf algebra, a bimodule analog of Hopf algebra, introduced by Etingov and Barchenko, and refined by Kerling and Rosengren. So let H be a finite dimensional C linear space, and blackboard F is a field of meromorphic functions on dual space H star. So firstly, we define the notion of H pre-algebras. So a tuple A, sigma tau, is an H plane algebra. If this A is an H star times H star graded C linear space. And each A sigma and A tau are graded F bimodules. There's no need to coincide both hand size actions. So such that the image of sigma and tau are commutative in the endomorphism ring of A. And for any small f in blackboard F and A in large A alpha beta, where A alpha beta means a homogeneous space with grading alpha and beta. So anyway, the left sigma actions and right sigma actions are compatible in this sense, and so is tau. Well, this symbol large T alpha means a kind of difference operator on blackboard F. That is, T alpha Fx is equal to Fx plus alpha. So the indeterminate x is shifted by alpha. And so the most fundamental example of H pre-algebra is a difference operator ring DH. So this space possesses an H pre-algebra structure if we set DH alpha beta homogeneous space is equal to Ft minus alpha if alpha is beta and 0 otherwise. And we also define the left sigma actions and right tau actions as a composition of a multiplication operator F from left side. So, and the important fact is the category of H pre-algebra has a monoidal category structure. In other words, we can define a tensor product, tensor children between two H pre-algebra A and B. So, note that the grading is not usual one, but rather, how to say, matrix product like one. So, anyway, so and the unit object of this category is a difference operator ring DH, just defined above. So we can define an H co-algebroid A delta epsilon as a commanoid object in this monoidal category of H pre-algebra. And the subcategory H co-algebroid also admits another monoidal category structure, that is the tensor product, tensor hat. So where the grading is just ordinary one, and the unit object is blackboard F. So as a result, we can define a notion of H by algebroid as a monoid object in this subcategory of H co-algebroid. So finally, we define the antipode of H by algebroid. So let H be an H by algebroid and a C-linear operator S on A. So this S is called as antipode if the following conditions are satisfied. The first two is ordinary, and the last two equation is separated so-called hexagonal axioms called ordinary antipode. So last expression is shifted, by the way. Anyway, so H algebroid is defined as an H by algebroid with this antipode. So, and the difference operator ring DH is also the most fundamental and important example of H algebroid. The co-multiplication and co-unit and antipode are defined as follows. So I also mentioned that if we set the grading space large H is 0, then we can recover the ordinary Hopf algebras from this definition. So in the sense, this H Hopf algebra is a generalization of ordinary Hopf algebras. So the general theory is over. And we came back to the elliptic quantum group situation again. So let UQP XL1 be the elliptic quantum group of type affine root system and non-twisted affine root system XL1. And set the grading space large H be as a C-linear, L-dimensional C-linear space expanded by only non-shifted dynamical parameter large P1 that is large PL. This space is isomorphic to causal subalgebra of type finite root system XL corresponding to this XL1. And we define the blackboard F as a field of meromorphic function on dual space H2. And define the moment maps, kind of algebra morphisms from formal power series F double bracket P to UQP X1 as follows. And we also said the F actions on this elliptic quantum group by the multiplication of the image of these moment maps from left and right. So elliptic quantum groups admit defining a relation I didn't mention before, like this: GP EIZ is equal to EIZ Z and so on. So these relations understood in terms of H-hop algebra, that is current EIZ lies in homogeneous space minus alpha I0, and FYZ is in 0 minus alpha I, and so on. So, and the modified tensor product, tensor tilde works as an exchange of dynamical parameters. That is, if we have shifted dynamical parameter large P plus H in left side, we can switch it to right side, removing the shift parameter H. And so we can same thing for elliptic parameter and shifted elliptic parameter. So to see how these structures works well, I will give an example that the Drinfeld type of multiplication preserves the defining relations of elliptic quantum algebra. So that is, I will prove this equation at the top. So let's apply the co-multiplication delta to left-hand side, and using exchanging relation between psi I plus and psi j plus, we can get the second equality like this. And recall that we can remove we can switch this right-hand side Gij star to left side, removing the shifted symbol star. Then we can get the third equality. And this is nothing but the right-hand side of the equation we want to prove. So any other relations can be shown in the same manner, and we can introduce a Hop algebra structure on UQPXL, elliptic quantum group. So, and as an application, we can study the representations of elliptic quantum algebra along with H-hop algebra way. So I think so. So to conclude, I will give summary today's talk. So first, the elliptic quantum group is defined as an elliptic and dynamical analog of the Drinfeld realization of quantum affine algebra, UQXL1. And H-hop algebra is a bimodule analog of graded hop algebra, admitting two tensor products, tensor tilde and tensor hat. It's corresponding to co-multiplication delta and multiplication mu respectively. And finally, an elliptic quantum group possesses this H-hop algebra structure. The F action is given by the multiplication of the meromorphic functions of dynamical parameter. And this is a reference. That's all. Thank you for listening.
Thank you for the talk. Any questions or comments from Nagoya? Question? Then how about the online? No. Then I have one comment or question. Yeah. So you begin in the beginning, you mentioned that these elliptic quantum groups and quantum affine algebras are related to R matrix.
Yes.
And you explained some very complicated algebraic structure of the
Yeah, I did.
elliptic quantum groups. How can we understand this, the relationship to these R matrix from the algebraic structure you explained.
Matrices and okay. So in this sense, this is very sensitive. Roughly speaking, elliptic quantum groups can be recovered from elliptic R matrices by FRST-like construction, but not usual, rather generalized FRST construction. That is.
So you mean that using R matrix, we can also using R matrix only we can recover these algebras in some sense. Through the FRST construction.
I can't say that's precisely that. So imprecisely, this construction recovers the elliptic quantum group in the sense of Felder, I think. And there is some little bit difference in the Felder's ones and these elliptic ones by Kono or the
I see.
Yeah. So, but roughly speaking, there is a equivalent or same thing. Yes, I think so.
I understand. Thank you for your comment. Any other questions or comments? If not, let us thank the speaker again. And this is the end of the today's afternoon session. And Hayashi Sensei, do you have some comments?
So maybe Kano-san will make closing remarks, I think.
Hi. Can you hear me?
Yes.
Okay. So I'm asked to say something as a closing remarks. So this is the end of the third Shenzhen-Nagoya joint workshop on quantum science. Followed similar workshops in the last 2 years. So on the behalf of organizers, I'd like to thank all the speakers for their interesting presentations. And I already know that the slides of some talks, some presentations are already uploaded on the web page of the workshop. I also thank all the participants, both online and on-site, in particular, those who contributed to communication with the speakers. And finally, as a member of Nagoya University, I'm grateful to Masahito Hayashi and Ansi Bai for all the effort for handling the matters on Shenzhen side. Okay, that's all. But I'd like to discuss some practical issue. In the last 2 years, we have this workshop in June, and this year, for some reason, we scheduled in early September. So I'm wondering how about the next scheduling of next year. Are there any feedbacks from the participants or on Shenzhen side, from Shenzhen side? No? Ayashi-san, do you have any comments on the scheduling?
Scheduling, so not only the scheduling, but also somehow organizing on the Shenzhen side is somehow not so good. So I need to more good arrangement to increase the participants from Shenzhen side. So maybe I need to make a more good idea to organize the Shenzhen side. So I think the participants from Shenzhen side in this year slightly small.
But this year, more institutions from Shenzhen side. I mean, more institutions are involved in Shenzhen side.
Yes, so due to that reason, somehow the research organization in Shenzhen side is diverse, not well concentrated. So this is somehow another problem. So not so easy.
Okay, I see. Are there any proposal or feedbacks from other people? No? Okay, so I suppose in the next year too, we will have a similar workshop possibly in September if we are planning to make a hybrid format workshop in this such a way. So it is very convenient from Nagoya side. It's very convenient to organize.
So I want to hear opinion by Li Jin.
Who?
Li Jin, do you have some comment? I want to hear your opinion about the organization. Li Jin. Do you
Sorry.
have some idea?
Are you saying me?
Yes, please. So for organization of this workshop.
Well, I don't have much. I don't have much to say.
Okay, thank you.
So in case, so we are going to organize a similar workshop in the next year, possibly in September. So see you again. Thank you very much for your attention.
So maybe it is better to talk some more informal way. So now I want to stop the broadcasting. So